All right, let's just jump right in. Water. We see it, we drink it, we use it every single day, right? We feel like we know it inside and out. But what if I told you that this super common stuff is actually hiding some of the biggest, most fascinating secrets in all of science? So let me just ask you this. What if the most common substance on Earth was also the strangest? I mean, seriously, what if the very liquid that covers most of our planet is actually the weirdest liquid in the entire universe? Because, a lot of scientists think it is.
And listen, that is not an exaggeration. Get this. Scientists have documented over 70, that's 70, physical anomalies for water. What does that mean? It means water breaks the rules of physics in more than 70 different ways. Nothing else we know of even comes close. So, what is going on here? Let's figure it out.
Okay, so the whole explanation, all of water's weird and wonderful properties, it all comes down to the secrets hidden inside one single tiny molecule. You know the one, H2O. I mean, it looks pretty simple, doesn't it? Just one oxygen atom, two little hydrogen atoms. But the key thing here, the really crucial part, is its shape. See how it's not a straight line? It's bent at this very specific 104.5-degree angle. And that simple little bend, that's the first clue to unlocking all of water's incredible power. So, because of that bent shape, and because the oxygen atom is a bit of an electron hog, the whole molecule gets this uneven charge. The oxygen side ends up being a little bit negative, and the hydrogen side ends up a little bit positive. It's kind of like a tiny, super weak magnet, with a plus side and a minus side. This whole thing is called polarity, and trust me, it changes everything. All right, so because all these water molecules are like little magnets, they don't just float around on their own. Nope, they interact with each other. They form this, well, you could call it a massive, constantly changing social network. And it's all powered by something called hydrogen bonds. And you can see how it works right here. The positive hydrogen side of one molecule gets attracted to the negative oxygen side of another one. Simple, right? But these connections, these hydrogen bonds, they're not permanent. Not even close. They are constantly breaking and reforming, billions of times every single second. It's like this frantic, nonstop molecular dance. So this constant connecting and disconnecting, this socializing between all the molecules, it creates a kind of stickiness. And this molecular stickiness, it's the reason for pretty much every single strange thing that water does. So what does all that stickiness actually do in the real world? Well, for one, it creates surface tension. It's so strong that it lets insects literally walk on water. It's also responsible for cohesion and adhesion, which lead to something called capillarity. And that's the amazing way water can defy gravity and climb up inside plants, pulling nutrients all the way from the roots to the very top leaves. Okay, so now let's build on that. Let's see how those tiny bonds lead to water's most famous rule-breaking behaviors, the very anomalies that make all life on Earth even possible. Okay, here's the big one. Almost every other liquid out there gets denser when it freezes. It shrinks. The solid form sinks right to the bottom. But water? Oh no, water does the complete opposite. When it freezes, those hydrogen bonds lock into place, forming a crystal structure that actually takes up more space. It expands, becomes less dense, and that's why ice floats. And this isn't just a cool party trick. It has a massive impact on the real world. You see, water is actually at its heaviest, its most dense, at about 4 degrees Celsius, not at freezing. So what happens in a lake in winter? That 4-degree water sinks to the bottom, while the colder water and eventually the ice stays on top, forming this perfect insulating layer. It's what allows all the fish and aquatic life to survive the winter underneath. Now check out this comparison. We've got hydrogen sulfide here. It's a molecule that's pretty similar to water, but it's almost twice as heavy. So it should have a higher boiling point, right? Stands to reason. But it doesn't. Not even close. Its boiling point is negative 60 Celsius. Meanwhile, water, which is way lighter, boils at 100 degrees. So what gives? It's all about the energy it takes to break that incredibly strong network of hydrogen bonds. And that same exact property, the way it takes so much energy to break those bonds, it also means water acts like the planet's thermostat. It's like a giant thermal sponge. The scientific term for this is high specific heat. Basically, water can soak up a ton of heat without its own temperature changing all that much. Think about it. Our oceans absorb massive amounts of heat, which helps stabilize the entire planet's climate. And our own bodies, we do the same thing. Since we're mostly water, we use sweating to regulate our temperature. It's a ridiculously efficient cooling system, all thanks to H2O. But water's weirdness isn't just about physics. Its molecular properties also make it the ultimate mixer. It's so good at dissolving things, it's earned the nickname the universal solvent. And this is absolutely essential for life. So, how does that work? Well, it goes back to that polarity we talked about, that tiny magnet quality. It's just perfect for grabbing onto and pulling apart other polar molecules, like salts and sugars. The water molecules then form these little cages around whatever they've dissolved, which is how our blood and plant sap can carry vital nutrients around. In fact, almost every single biochemical reaction that keeps you alive right now is happening inside water. Okay, quick question. We all learned this in chemistry class, right? Pure water has a pH of exactly 7. It's the definition of neutral. But is that always true? Believe it or not, the answer is no. As water gets warmer, its pH actually goes down. So for example, at 50 degrees Celsius, pure water has a pH of around 6.6. But here's the twist, and this is the important part. It's still perfectly neutral. Why? Because neutral isn't about hitting the number 7. It's about having a perfect balance between acidic and alkaline ions. And in pure water, that balance is always maintained, no matter the temperature. So when we see water sitting there at pH 7 on the scale, what we're really looking at is a snapshot taken under very specific conditions, usually 25 degrees Celsius or room temperature. It's our baseline, our reference point for neutral, but it's definitely not the whole story. And just when you think you've got this all figured out, there's one last little twist for you. The water we use every single day, it isn't actually just pure H2O. You see, a tiny fraction of the water in your glass is actually something called heavy water, or D2O. In this stuff, the normal hydrogen atom is replaced by deuterium, which is just a hydrogen atom with an extra neutron. It seems like a tiny change, right? But look at this. That one little neutron completely changes its fundamental properties. It freezes at a higher temperature, it boils at a higher temperature, and its point of max density is way off from normal water. It's wild. And that really brings the whole thing full circle, doesn't it? It all starts with that simple 104.5-degree bend in one tiny molecule. And from that, all of this incredible complexity just emerges. Floating ice, stable climates, the very chemical reactions that make life itself happen. So I want to leave you with this one thought. The next time you pour yourself a glass of water, are you going to see just H2O, just a simple, clear liquid? Or are you going to see what's really there? A dynamic network of trillions of tiny magnets all engaged in a frantic dance. The strange, the rule-breaking, the absolutely wonderful molecule that makes our world and our lives possible.